So good morning, everybody, and welcome to webinar number 8 of our Powerful Knowledge series. Today, my name is Ian Mosley, and today we have Jose on the line, who is going to be taking over this presentation to discuss some fascinating aspects of silicon carbide power MOSFETs, and in particular the instabilities you can sometimes see in gate threshold behaviour. Now, this might seem like quite a niche subject, but actually it's critical to understand these sorts of effects to be able to fully exploit the capabilities of these new types of devices. This webinar will be about 1 hour long, something like that, and we have a Q&A session at the end. If you do have technical questions as you go, we have a questions box on the right-hand side. Please type your questions in there. There's also a chat box. If you have any issues on technical issues on being able to view the webinar or something's not working, type that into the chat box and I will try and resolve any issues there. We'll also be conducting some polls as we go through this webinar today to help Jose understand some of the stuff that you know about in terms of these gate oxide effects. I think that's probably it from me. We'll have the question and answer session at the end. I look forward to chatting to you then. So, Jose, it's over to you.
Hi, so welcome to the webinar. So let's start. Just going to disable the webcam. Share. So there we go. So welcome to this webinar, part of the Powerful Knowledge series. And this webinar is called Gate Oxide and Threshold Voltage Instabilities in Silicon Carbide Power MOSFETs. This is just the outline of the presentation. We start with an introduction, then we cover a bit on threshold voltage instability in silicon carbide MOSFETs. We evaluate the implications of bias temperature instability, that's another way of calling threshold voltage instability, on the electrical parameters. We show a bit on characterization of bias temperature instability, and we just conclude the paper and acknowledge the people who work on this and the funders. So we know that gate oxide was a reliability concern in silicon carbide MOSFETs. There are plenty of studies in the last years, from the beginning when it was more of a problem than now that things are solved. So things have improved considerably. So the key of this performance is just the semiconductor oxide interface. And the silicon carbide silicon oxide interface is not silicon oxide. It's a more complex interface. So we have the wider band gap of silicon carbide, 3.3 electron volts, and the narrower band offsets to the dielectric. We also have the existence of carbon, and we also have the interface and near oxide trap densities that are 100 times larger in silicon carbide silicon oxide than in silicon oxide. So here you just can see a MOS interface with the oxide, metal oxide semiconductor, and you can see the oxide trap. There are oxide trap charges, mobile ion charges. Then you have charges in the interface between the semiconductor and the oxide, and they are the densities of these traps, and near the interface they are larger in silicon carbide silicon oxide. So a way of testing the quality of the oxide is just time-dependent dielectric breakdown tests. So you just bias the gate until the oxide breaks, and this is just a matter of applying an electric field until you get the wavelet distribution, so you just get the time to failure. And this is determined by the intrinsic and extrinsic defects of the oxide. So you have extrinsic defects that are related to contamination, processing issues, and different stuff like particle inclusions, porous oxide, substrate defects. And then you have intrinsic defects that are related to the material properties themselves. Things have improved, just the quality of the oxide, better processing, so you get a most reliable oxide that managed to survive higher electric fields that are also related to the thickness and during more time. So you can just see this kind of extrinsic defects that can appear on the oxide. So would like to highlight that different studies had shown a reduced reliability of the gate oxide and silicon carbide MOSFETs. This was more apparent in the first generation devices, and the manufacturers have reported a lot of improvements in the later generations. So you can bias the devices with high voltages, but you have to be aware that things are happening. People change the ratings. The ratings are not the same in silicon carbide and silicon, and it's easy to do a literature check and verify the latest studies and improvements that the manufacturers have done, different research groups that are working on the topic. So that's always interesting to do if you're interested in this topic. So I have a question here. So Ian, if you can launch the question. Thanks. So as I was saying, there are a lot of examples in the literature. I have some here, but there are many more. I would like to highlight this. This is a free article. You have threshold voltage bias temperature instability in commercially available silicon carbide MOSFETs. And they just compare different devices that they were first generation and later generations, and you can see the different performance. And in the second one, they just analyze the breakdown of the gate oxide of different silicon carbide and silicon IGBTs. They are compared. And some papers that they explain properly the concepts of BTI, characterization methods. They do a review focusing on reliability. So that's interesting. If you are interested, I will recommend you to go through these papers. We'll try to do my best explaining some concepts during this webinar. So I have to refresh a bit the first webinar. And it's important to mention that the gate insulator is not perfect. So first thing that I would like to highlight is that the gate leakage increases with temperature, and that the gate leakage is also in silicon carbide greater than silicon. So here we have two devices. One device has greater leakage currents. So if you bias the device with 30 volts, you already have a lot of leakage current. The other device, you have to go at 35 volts to get similar gate leakage levels. And the gate leakage current increases with temperature. And then if you compare silicon carbide and silicon devices, silicon carbide devices are leakier than silicon devices. So this just tells you what happens when you apply an electric field, a gate voltage to the oxide. But stressing the gate does not only break the device. You have something called bias temperature instability, which is the shift of the threshold voltage caused by biasing the gate, by applying that gate voltage to the device. And what's the threshold voltage? The threshold voltage is just the gate voltage that you require to invert the channel, to raise the MOSFET surface potential to twice the bulk potential. And you have this basic equation textbook here. And what you can see here that some is dependent on the doping density, intrinsic carrier concentration, the gate oxide, capacitance. But most important is that you have the charge in the oxide. So this is key. If you have more traps in the oxide and you're trapping charges, this is going to affect your threshold voltage. And that depends if they are positive charges or negative charges. So what happens if effectively you are trapping charges in the oxide? We can verify that just using high temperature gate bias test. Just consider highly accelerated. You apply a high voltage to the device, and you will trap charges, and you will see what happens with the transfer characteristics. So that's here. So you have an IGBT. You apply plus and minus 40 volts and at 150 degrees. You check the transfer characteristics after 5 hours relaxation, everything at ambient temperature, and you see that there is no impact on the transfer characteristics. You do the same in silicon carbide. Still, this is very accelerated. You're applying 40 volts, which is a lot for this device. And if you apply a positive voltage, you shift the threshold voltage up. So it's a rightward shift of the transfer characteristics. If you apply a negative voltage, you shift the transfer characteristics to the left. So you have a threshold voltage shift in silicon carbide at these gate voltage stress levels that you don't have in silicon IGBT. So that's the interface is different. Interface is a bit more complex. So let's just define some terms. So you have threshold voltage instability, also called bias temperature instability, BTI. You will see that terminology applied differently. So MBTI is negative bias temperature instability, and means that a negative gate bias causes a negative shift of the threshold voltage due to the capture of positive charges in the oxide or the interface. PVTI is a positive bias temperature instability. That means that the positive gate bias causes a positive shift of the threshold voltage due to trapping of negative charges in the oxide or the interface. Increasing the stress voltage increases the shift of the threshold voltage. So if you apply a greater voltage and you're not breaking your device, you will shift your threshold voltage more. This BTH shift recovers after stress removal. So those traps are trapped, those charges are trapped and released. And this recovery is accelerated if you bias the device with a gate voltage that is opposed to the stress. So something that has been identified in silicon carbide is something called hysteresis of the threshold voltage. And it means that the sweep direction affects the threshold voltage measurement. And this is because you have interface traps with fast time constants. So if you bias your device upward, so from 0 to 20 volts, you are trapping charges, you are shifting the threshold voltage up, and then you stay there for a bit, and then you go back. When you do the measurement from positive voltage to 0, you will see that the threshold voltage have shift. There's a positive shift. So that's hysteresis. And this is just because you have interface traps that they are really fast to capture, and just during the measurements they can be captured. Sorry. And you have something that is called recoverable shift linked to the hysteresis, and then you have a more permanent shift. It's important to say that this can affect the electrical performance. So the electrical parameters are affected by BTI, so losses, reliability implications. And it's also important to say that this has to be properly characterized. You have to define stress and recovery sequences, proper measurement sequences, and then you have to define suitable methodologies for silicon carbide MOSFETs. So some questions that we'll try to address in this webinar is, what's the impact of BTI on the device performance? And what about the peak shift and recovery of BTH after stress removal? Can we characterize that? Can we understand what's going on? So those are two questions that we will try to address in this webinar. So let's go now with the threshold voltage instability in silicon carbide MOSFETs section. So bias in the gate causes a threshold voltage shift. And when do we bias the device? So you bias the device when you are doing high temperature gate bias tests for qualification. So like this, you just apply a gate voltage to the gate for a long time, 1,000 hours. So that's going to change the threshold voltage of the device, and you have to capture that properly. Then power cycling, the circuit here. Usually you just apply a positive gate voltage to the device under test. The device is always on, and you control the current with an auxiliary device. So if the test runs for 3 weeks, you are going to apply 15, 20 volts, the nominal gate voltage to your device for 3-4 weeks. That can affect the threshold voltage. And then also during normal operation, you're going to have switching stages and standby stages. So switching, people are now reporting that also causes a switch-induced threshold voltage shift. And you also have the standby stages. So you have a gate voltage of -5, and your converter is off for 1 day, 2 days. You're going to have your gate bias with -5 volts. So that's interesting to know what can happen there. BTI, it already existed in silicon devices, but it has been more challenging in silicon carbide MOSFETs. So it's just a more complex semiconductor oxide interface. That higher density of traps, the bandwidth, and the band offsets that are smaller. So there have been improvements in the new generation devices. So it's important that people know that this problem was there, and they have been working in the new generation devices. So things have changed. So it's the high oxide quality, better material processing, better screening. But there are still some issues to tackle. I would say proper characterization methods. It's an active area in 2018, 2020. And evaluate the qualification implications of this phenomenon. So a way of testing BTI, and it's a test that is easy to do, and you can do that in your lab and check what's going on, is just to accelerate the stress test. Just applying a high gate voltage at high temperature, and then just apply a recovery. You just want to characterize the permanent shift if you want to see what happens. So you can apply positive and negative gate voltage. You short the drain and the source. And just with basic lab equipment, you can just stress the device. So you can do this for PVTI. We have done some cumulative gate stresses to see what happens with the threshold voltage. And we evaluated the input and the transfer characteristics. Everything was measured at ambient temperature. So we use a Cure tracer 16 hours after the stress. The device was biased with a gate source voltage of 0. So once we know that we are only going to characterize the permanent shift, we tested different devices. If you increase the stress, 25, 28, 30 minutes, 30, 32, so you can see how increasing the oxide stress shifts the voltage up. This is PVTI. And the other device, we did 35 and 40, and you also see a positive shift. So this is permanent shift after this long recovery time, or I would say a more permanent shift. You can do the same for negative gate stresses. Again, cumulative gate stresses. We again evaluated the input on the transfer characteristics following the same procedure of 16 hours relaxation, and it was also measured using a Cure tracer. So we have the stress values here. It was minus 25, minus 30 in 2 stages of 30 minutes, and you can see how the threshold voltage is shifting down, so leftwards. You can see a initial shift, then just a bit, and then if you increase the stress, it shifts a lot. And in this device, you can see that minus 40 volts, which is a lot, probably 8 times the rated voltage. So you can see that there's a massive negative shift. So that's why, if you remember silicon devices, the rating is positive and negative the same. So in the case of silicon carbide, the rating identified on the datasets, they are different. So this probably gives you a clue about this. So this also will affect the output characteristics. So from the stresses, go back to this figure with the positive and negative. You can characterize the output characteristics, and things are more apparent at the lower gate voltages. So you can see if you drive your device with 16 volts, it's not that apparent. But if you drive your device with 12 volts, things become really apparent. So the changes in the output characteristics, they are considerable. Same with MBTI. 16 volts, that's not that much, just marginal. But if you check that at 12 volts, there's a massive change in the output characteristics of your device. So let's evaluate now that we know that BTI happens, that it affects the transfer and output. What are the implications on the electrical parameters? So the first thing is that it affects the threshold voltage. We have shown that it affects the output characteristics. So that's the on-state resistance. Let's analyze this a bit in detail. Let's make some approximations. So in a silicon carbide planar MOSFET, so you can approximate the on-state resistance like the sum of the channel resistance, JFET, and drift resistance. That the drift resistance is just the resistance of the drift layer that you require to block voltage. In a trench MOSFET, you don't have the JFET resistance, so it's just mainly channel and drift resistance. This is for a 1200 volts high voltage, medium voltage silicon carbide MOSFET. If you increase the voltage rating, this resistance is going to dominate. So in a 10 kilovolt MOSFET, this is going to be more dominant, the drift. Let's analyze now a bit the channel resistance, which has a key role in these voltage ratings. So you see that the threshold voltage appears here. There's the mobility, but let's assume that this is at constant temperature, so parameters are constant. So you have BTI and you change the threshold voltage, you are going to change the channel resistance, which is important component on the total on-state resistance. So if you reduce the threshold voltage, the channel resistance is going to decrease. If you increase the threshold voltage, it's the opposite. And then this is the role of the gate voltage. If you increase the gate voltage, this is going to be smaller. If you reduce, this is going to be larger. And this shift is going to be more apparent. So let's analyze the on-state resistance itself from the transfer characteristics. So we know that it increases with PVTI. This will cause increased conduction losses. And it's more apparent at low gate driver voltages. It's just, as I mentioned, the role of the channel resistance. So here we have some cumulative shifts, and you can see how the output characteristics are being shifted. So you can see the increase of the on-state resistance, I would say more apparent at low gate voltages. So you see, go to the 20 amps, 18 volts, that's not very apparent, but if you go to 12 and 14, that becomes apparent. So just calculating the on-state resistance slope, you can see that for 18 volts, there's a positive shift, and for 12 volts, that shift it becomes higher, more apparent. Check that this is logarithmic scale. Also, this is good to explain a question that was in the first webinar, that it was that if the resistance is dependent on the load current, it's just the slope of this. So if you check, when you're driving your device with 18 volts, it's marginally current dependent, so it increases just a bit. If you're going to work from 3, 4 to 10 amps, 15 amps in this range, you can say that it's not the impact of the load current is not high. But if you're driving your device with low voltages, the on-state resistance is very dependent on the load current. So let's see now what happens with MBTI. So the on-state resistance, it decreases with MBTI. So you can see shifts to this point, so the slope increases, so that's lower resistance. And this will cause reduced conduction losses, which you will say, oh, this is good. My device is going to have lower on-state resistance, lower power dissipation, but it also can be an issue if you have parallel devices. This is just can lead to thermal runaway. And moreover, this can aggravate parasitic turn-on. If you remember the previous webinar, if you reduce your threshold voltage, the susceptibility to parasitic turn-on is going to increase. And similar to PVTI, sorry, this is more apparent at low gate driver voltages. Again, the role of the channel resistance. So you can see at 18 volts, when you're driving your device properly, this is not very apparent, just a slight increase. But when you're driving your device with low voltages, things become really apparent. So this is a massive reduction of the on-state resistance. So it looks like that this is the area where BTI is going to be more apparent. So let's analyze the impact of the gate voltage on the on-state resistance. So we just measure the on-state resistance at low currents as a function of the gate voltage for a unstressed device and for a stressed device. And you can see that at 18 volts, the input of when you're biasing the device with 18 volts, the input of BTI on the on-state resistance is not considerable, probably it's around 5%, something like that. But if you reduce your gate voltage, things become really apparent. If the channel resistance dominates the total on-state resistance, just check how it can reduce by a half in the case of MBTI. It can increase, I would say, around 30-40%, looks like 30% at 10 volts. So it means that the gate voltage is fundamental for understanding and driving silicon carbide devices. Again, you want to be here, but that can have a reduced lifetime at your gate oxide as well. So you need to understand limitations and trade-offs. What happens now with the transients? So we have shown just static characteristics. What happens with the transients? So there's a shift of the threshold voltage, and that leads to a shift also of the gate voltage plateau. Let's refresh a bit the transient to see what's the threshold voltage and the plateau. This is just related to the turn on transient. So the threshold voltage is when you have current, and the plateau is the voltage where the drain source voltage decreases and when you have reached the load current. So if the threshold voltage shifts down, up, this is PVTI. If the threshold voltage shifts up, the gate plateau is going to shift up. So we characterize the switching transients, and you can see that PVTI shifts up if you're doing PVTI, if you're doing a positive gate bias stress, and this is easily observable in the transients. You just reduce your switching rate in order to make this more apparent, and you can see how the plateau increases. Also, this means that the switching rates are going to be affected. Just going back to this, it's just the time between BGP and BTH. This is where you have the current rise. So if those values are going to change, it can be affected. So this can lead to switching losses. This can have impact on parallel connected devices. If you just analyze the equation of DIDT, threshold voltage appears there, so DIDT is going to be affected. So PVTI reduces the switching rates, MBTI increases the switching rates. We are working with gate voltages and resistances that we can exaggerate this, but you can see that there's a clear change in the switching rates because of this threshold voltage instability. Again, this was a highly accelerated stress of 40 volts. And this is quite important. So I have to go back to the body diode voltage. So if you remember, there were in silicon carbide MOSFETs in the third quadrant, you have current flowing through the channel due to the partial turn on during reverse conduction. When the gate source voltage is 0, it's just to connect the gate and the source. So 0 volts. You have current flowing this way. So there's a relative voltage lower here. This is 0. This is in order to have conduction. You have a drop. So you're going to, this is like partially turning on the device. You're going to have current flowing through the channel. So this is like a current divider. What happens if the threshold voltage changes? So this partial conduction is going to be affected. So let's analyze what happens in the case of PVTI, the positive shift of the threshold voltage. This will affect the third quadrant voltage as well, third quadrant characteristics. So if this increases, this means that your channel is going to be more difficult to turn on. So there's going to be more current flowing through the diode or less current flowing through the channel. And you start seeing a higher voltage as there's more current flowing through the body diode. So what happens in the case of negative stress? In the case of negative stress, so you have a negative shift. So that means that your channel is going to be easy to turn on. So that means that you have more current flowing through the channel. So your third quadrant characteristics are going to shift to the right. So you're going to have a lower PSD voltage. This is just a matter of the current divider. Now, something that I would like to highlight here, now from these characteristics, you know that this is what is used as TSCP in power cycling, the voltage, VSD voltage at low currents. So it's easy to understand one of the main challenges of power cycling silicon carbide MOSFETs that people have sorted out recently. So if VSD is used as a temperature indicator during power cycling test, is it affected by BTI? Can we minimize the impact of BTI? So you have to be sure that when you're doing power cycling and you want to determine the junction temperatures, you have to be sure that your thermometer is accurate. Otherwise, you are not getting good results. We verify that in the case of PVTI. So you apply, this is just your calibration curve that gives you temperature as a function of PSD, or PSD as a function of temperature, as is plotted here. If you're using BGR0, you can see that there's a positive shift in both cases. But if you close your channels, so you apply a negative voltage, you minimize the impact of the positive shift. So your K curve remains constant. So this is a way of minimizing the impact of PVTI on the calibration curve of the during power cycling, so K factor. MBTI is not that easy. At PGR0, you have a massive shift. If you apply a negative voltage at -4, you reduce that, but you will require a higher voltage to close the channel. So, but usually don't worry too much about MBTI. During power cycling, you care more about PVTI, and this is what people are recommending, that you have to apply a negative voltage to be able to use the body diode voltage as a temperature sensor. So I have a question here. That is question number 2. So instead you have used power cycling in silicon carbide MOSFETs and you were aware of this. So we have evaluated what happens with PTI and the electrical parameters. Let's go now with characterization of PTI. So until now, we have only studied highly accelerated stresses. The key was applying a high gate voltage to be sure that there's a permanent shift that we managed to detect, and a long recovery to minimize transient effects. During the test, we are noticing that there were cases that, there's no apparent shift. So is that real? Is that something that we are missing? So this was when we were starting working on this. So you can see here like -10, -30, there's no shift. Is this something that we are not shifting the threshold voltage, or is there any kind of recovery mechanism there that we were not aware? So that's what's happening. So the threshold voltage, once you remove the stress and you bias the device with 0 volts or with a negative gate bias, you're going to, negative in the case of PVTI or positive in the case of MBTI, you're going to shift the threshold voltage. So that's key to understand and to characterize, to be sure that you are characterizing and determining the real shift. So methods for VTH characterization after gate stress removal are required, and there is plenty of activity. So key here is characterizing the peak shift, and this may have qualification implications. Imagine that you are testing a device and 1,000 devices, 20,000, we'll say 1,000 is standard value, and then you are doing the stress 1,000 devices at the same time, and then you have to characterize them. From the moment that you characterize the first to the moment that you characterize the last, some time may last, and you may miss that peak shift. Also, you have the role of temperature, so you have delays between stress and measurement. You have the hysteresis, it is recoverable, and the more permanent shift. What do you worry more about the hysteresis, the more permanent shift, which one is more application relevant? There's a lot of work ongoing on those topics. And then you have that the measurement method affects the threshold voltage measurement, also the sweep direction, delay between stress and characterization. So there are a lot of variables that will affect your threshold voltage measurement in this kind of tests. Some methods have been proposed in the literature. So there's a nice overview. So you can check if you are interested in this. Some people are proposing a precondition method that you just apply. If you're going to do, for instance, if you're going to do PVTI, you apply a negative pre-stress. So you are sure that they define the initial state of charge before and after stress, so you can characterize that. Some people are proposing capture emission time maps and very fast AC stresses. And this is a nice review where they compare all the different methodologies. They show the implications of using slow methods and that stuff. What's the comparison between using one and the other? So there is a lot of activity there. So if you are interested in these methodologies, these are good papers to check. And then the role of the threshold voltage shift in power cycling has also been evaluated. So, this is not the right. I have to copy that. Apologies for that. I just copied the other one. Sorry. So I have a question here. Have you been studying this or were you aware of this? So we have done our work on this topic, and we have done our, let's say, efforts in developing some methodology, some characterization methodologies, and we have presented one based on the body diode when the gate voltage is 0. This is similar to the use of BSD as temperature sensor, but for detecting oxide degradation BTH shifts, calibration is required, and this can be done using accelerated stress test. So if you remember the body diode voltages during as temperature sensor, if you know that if your temperature is fixed, let's consider that at ambient temperature, there was a shift of the BSD. So you can link that relationship between BTH and BSD, and you get a nice relationship. You just normalize that, and you have the relation between BSD at a fixed temperature and the threshold voltage. You also have the same, these are for two devices, so you have to calibrate this for each device, as the devices are different, if you're going to use devices from different manufacturers. So you have different calibration relationships between BSD and BTH. The circuit is just like the use of BSD as TSEP. You just require a gate driver to apply the stress voltage to the gate. It can be positive. You can do slight modifications and do negative. You can control the stress duration. So you can also adjust the temperature of the device. And then you just need a constant current source. It's a low sensing current flowing in the source drain direction. You just need a basic equipment to adjust the pulse duration, capture transients. And that's it. Let's see what happens if you apply this methodology for characterizing threshold voltage shift. Are we able to characterize the peak shift and recovery? So these are the PVTI evaluation results. So you have three different phases. You have pre-stress phase, stress phase, and recovery. So this is just a 10 seconds 20 volt stress, so 0 to 4 volt to 4 seconds. Gate voltage is 0, is the pre-stress phase. The current will flow through the body diode channel as a function of the initial threshold voltage, so we have around 1.5 volts. And we can say that this is the threshold voltage. We just normalize that. So you have a value of 1. Then during the stress phase, in this case it's 10 seconds of 20 volts, you apply a gate voltage of 20 volts, you turn on your device and the current will flow through the channel, so your voltage is going to be really low. You have on-state resistance times the sensing current. So you don't know what's the threshold voltage during the stress phase, but once you stop the stress, the gate voltage is 0 volts again, so you can have the current divider and the current will flow through the body diode and the channel. If your threshold voltage has changed, your the current divider is going to be affected. So if your BSD increases, that means that you have more current flowing through the diode. And that's what you observe here. So a positive shift of BSD. So that's the peak threshold voltage. And now you have your gate bias at 0 volts. So that means that your threshold voltage is going to go down. If your threshold voltage goes down, you will have more current flowing through the channel or less current flowing through the body diode, and BSD reduces. As you have the relationship between BSD and BTH, you can track the recovery. So you can characterize the variation of the threshold voltage, initial peak, and you can track the recovery. And you can see that 4% shift after stress removal goes down to 2% after probably, let's see, around 24 seconds. What happens with MBTI? So we do the same. We have a slightly modified gate driver that is 0 to minus 26 volts. We again have the same stress phases, 0, minus 26, 0. You have the initial BSD. You have the stress and recovery. So during the stress, everything is the same except the stress and the recovery. Let's see. You start with the first pre-stress. Everything is in the steady state. Then you apply the stress, minus 26. Key here is that the current flows only through the body diode, and you will see a voltage that is equal to the PN silicon carbide PN junction, so 2.7 volts approximately. And then when you remove the stress, the current will flow again through the body diode channel. If you have shifted your threshold voltage down, more current should flow through the channel, BSD should reduce. And you see that it has reduced. In this case, it's around 70, 80 millivolts. And then during the recovery phase, BGS is 0. If the threshold voltage goes up, BSD goes up. And you can see that here. You have the peak and then it recovers, and you have a very, very fast recovery. So it goes down to -6%, and in the first seconds, it has recovered a lot. So that means that the transient effects in BTI, they are really important. So if you are characterizing this after 30 seconds after stress removal, okay, there is no shift. If you characterize this just some milliseconds, microseconds, you can see that the shift is higher. So this is why these things are important and methodologies are required. Silicon MOSFETs, as there is no apparent body effect, you cannot detect this. So you can see that there is no change in BSD after stress. So you apply 17 volts, nothing there. You apply -16. There's no change in the BSD. In conduction, you already have all the current goes through the body diode. So that's peculiar of silicon carbide. What happens if we do bipolar stresses? So a stress of 22 volts and a recovery of -10. So -10 plus 22. So you can see you go between 2.7 volts. The device is on. And then when you remove the stress, you go back to -10. And if you check, there's no apparent shift. BSD is not changing. And this is just with -10 volts, your channel is fully closed. So you don't see that change in the threshold voltage, and you don't have that current divider. So this is not something that was in the circuit, that is a transient effect. It's just the different current ratios between the channel and the body diode. So closing the channel, it means that you only have current through the body diode and you don't see the shift of the threshold voltage. Important in this test methodology is self-heating. So BSD is also temperature dependent. So you have to evaluate the role of self-heating during this test. And we have done this for positive stress. So during the positive stress, your device is on. So you will have very low current on state resistance. Self-heating can be neglected during the stress. Negative stress, so BSD is going to increase. You're going to have 2.7 volts, something like that. And low current, you can have some minor self-heating, and this can be relevant for long duration stresses. So it's important to monitor the temperature of the device at some heat sinks and monitor that your temperature is not increasing. So we monitor the temperature during the stress, 15 volts and -15, 16 volts. You can see that in 10 seconds, you can see that the input is just around 0.1 degrees. So here you can see when you have -16 volts, temperature rises 0.1 degrees as well, and then when this is 0. So if you consider 0.1 degrees, temperature sensitivity of BSD as temperature sensor is around 3 millivolts per degree. So you're talking about 0.3 millivolts, 300 microvolts, and we are talking about 70 millivolt shifts. So that shift is not caused by temperature. You can also characterize the recovery constants as you have different trap charges. So if you track your recovery, you can see differences between devices. So we just applied the same stress to different devices. So it was 20 volts, 10 seconds. And you can see that one device, the peak. So that's interesting. If you manage to monitor the recovery transient, you can see the time constants of the capture traps. So this is a benefit of this methodology, that you can do this directly. We also evaluated the stress magnitude. So we selected different devices. We have 4 different devices, and we applied a 15-minute stress of 22 volts and 32 volts, -16 volts and -26 volts. Just to evaluate, okay, if I increase the stress, I increase the shift. So you can see that in the positive stress, increasing the stress increases the shift, and then it recovers. Recovery looks like it's not affected in the positive stress. There's a change of slope. Already you have fast traps and slow traps that they contribute to the threshold voltage. With the negative stress, minus 16 volts doesn't cause a larger shift, but then if you go to minus 26 volts, the shift is massive. But it still recovers a lot. So this is around 30 minutes recovery. So you just check the recovery. You also see the different slopes. So this is something good of this method, I think, that you can manage to understand what's going on in the interface. You manage to capture the time constants. So that's always interesting. And this is another benefit, that you can use pulse stresses really easy. This is relevant to power cycling. So we have done 40 pulses of 2 seconds stress, 2 seconds PGR 0. Silicon MOSFETs, nothing is there. But silicon carbide, let's see what happens, 6 volts, 22 volts. So you can see there's an initial shift, and then kind of plateaus. During the 2 seconds recovery, it recovers slightly. And then when you finish the sequence, continues to recovery. So you can see that the initial shift is caused at the beginning, so 2 seconds is still a long pulse. 22 volts, that peak shift is larger. Then it recovers a bit more, so probably there are more traps. And you can see the same, so increasing the voltage increases the shift. This also applies to MBTI, so we did the same. Minus 26 volts. This is just PST. You can see a progressive shift. You could see that in PVTI it was plateauing, but here you can still see a gradual shift. And again, we are using accelerated stress test. This stress voltage, minus 26, is way higher than the rated voltage. I mean, we just want to see the phenomena. This is not about checking the reliability of the device. So we are just using stress voltages that let us to understand what's going on and characterize. So I have some questions here, question 4 and question 5. So yeah, if you can launch the questions. Thanks. So some limitations of this methodology. So it's nice, but it also has some limitations. First, it requires calibration. Then you have the temperature dependency of the calibration curve, that you have to consider that. And then it's not applicable when an anti-parallel Schottky diode is used in the device. The same happens with power cycling. So you have a Schottky barrier diode. The current will flow through the Schottky barrier diode, and that says if that happens, it means that you cannot use that parameter. Some people, for doing power cycling, they just cut the wire bonds to remove the Schottky barrier diode from the path. So just concluding. So we presented the concept of BTI in silicon carbide MOSFETs. We studied the impact of BTI on electrical parameters of silicon carbide MOSFETs, including static and dynamic. And we presented the use of the body diode voltage as a method for BTI characterization. So just acknowledgements. I would like to acknowledge Professor Laia Latisse and Professor Phil Moby. Thanks to the UKRI for giving me the opportunity to present this webinar, and thanks to the EPSRC and Power Electronics UK for funding this research. So I'm open to questions now. I hope that you enjoyed the webinar. Thanks for attending.
Thanks, Jose. That was a fantastic presentation. Some really good detail in there that is very relevant to successful use of silicon carbide. We do have a couple of questions coming in. I've also got a few questions that your presentation has prompted, but perhaps we can deal with the questions that have come into the question box so far.
Okay, so the first thing, does BTI effect have uniform characteristics, or it varies by device? It changes a lot between devices. So some people have reported that. One of the papers that I cite there, one that is Thomas Eichinger in microelectronics and reliability, they test a lot of devices from different manufacturers. So I think I closed that, but I can go back to the presentation. and they analyzed different devices from different manufacturers. And some manufacturers, the difference was not large, but in some devices, there was a big difference between devices. So let me try to find a paper I want to mention.
And it's just whilst you're finding that, Jose, the papers you've mentioned in your presentation today, are they all open access so the registrants can find those online?
Some of them are open access, some of them no. Some of them are in the institutional repositories.
Okay.
So if they just search the name, they can, I mean, our papers are in the institutional repository.
Okay, cool.
So sometimes they can access that. Some of them, if they were open access, I mentioned that.
Okay.
So that depends a lot on the device. You will observe that some devices, they have different. Let me just share this again. Share screen, application window. So this paper, the one that is threshold voltage peculiarities and biased temperature instabilities of silicon carbide MOSFETs, seeing microelectronics reliability. They show differences between devices. They done a lot of tests there. So can the MBTI be modeled to improve the model accuracy? Some people are proposing models and how the traps are charged and that stuff. So that's there's a lot of work there. But what I haven't seen, at least to my understanding, is if that can be added to the device. I mean, that can be a really good thing if you manage to add BTI to your SPICE models.
Mm.
So that can be an interesting topic. I know that people are trying to model that. So if you just do BTI search, you will see what a lot of people are working on that.
Yeah, fascinating.
And then another one, what is the forward voltage drop of a silicon carbide device? So that depends on the applied gate voltage. So if you apply 0 volts, you should see a low voltage. That is not the silicon carbide PN junction voltage. But if you apply a negative voltage, it plateaus. That's in the previous webinar when I was explaining that. So it's just around 2.7 volts. That's the silicon carbide PN junction voltage. It's the wider band gap. So I would say 2.7, 2. Also, that's on the, you can say that on the data sheets. Okay, there's another question. Have I done gate loss analysis for silicon carbide device? No, I haven't. It can be interesting to see if the gate loss increases, but not sure what will happen if the gate leakage current is going to be affected. So you will have to monitor the gate leakage current during the stress test to see what happens during the.
I guess there's two parts to that. There's the leakage current, which would be like a static loss mechanism if you've got a non-zero gate drive voltage. But then there's also the power consumed in actively driving the device during normal operation. And I remember from the previous webinars, I think it was the last one, we were talking about driving silicon carbide MOSFETs and the fact all of them have this sort of inherent internal gate resistance. And I guess that's where the majority of the power loss would be dissipated within the device during normal operation.
You have but there's no current when the device is fully on. It's a MOS device, so you don't have current. So unless the gate leakage current increases a lot, and you can have problems there. It may happen that your delay times are affected if your threshold voltage and plateaus are affected. So that probably means that you're going to have issues there.
Yeah. And I guess, sorry, carry on.
I would say, so in some of the papers, they report a massive hysteresis value, and they say, oh, hysteresis is not a problem. So when you have 1 volt, 2 volts during BTA change due to hysteresis, that's not a problem. So because it recovers during the switching cycle. So at the end, you don't worry. You shouldn't worry a lot about that. You should worry more about what's the name, the permanent shift. You should worry about that question there. That was a good question. If they are not balanced, I disable the camera. Otherwise, we lose a lot of.
Yeah, sure. I was just going to say that if you approach this from an application and power supply designer perspective, it's always a little bit worrying if the gate threshold voltages are changing throughout the life of your product, because you might go ahead and design it and then have problems further down the line. So I think what we're seeing as silicon carbide technology matures is that these effects you're describing, Jose, the BTI effects, the efforts are going in to stabilize those effects so that you can treat them as more constant. Would that be a fair representation, or do you think there's still a long way to go?
I would say people are aware, they have improved a lot. So if you compare devices, in the first devices, they were reporting the shift was massive. No, people know that things are there. If you just check the latest application notes from different manufacturers, they are aware of that, and they tell you have to assume this. They even, in one manufacturer, they give you lifetime as a function of the applied gate voltage during switching.
Okay.
So they know what's going on. They tell you cannot apply this, you cannot apply that. So
I remember from the early days of designing with silicon carbide MOSFETs, the very early data sheets didn't really, because the technology was new, I guess, they didn't particularly flag the fact that you shouldn't sit with a negative gate drive voltage, for example. So what I've seen over the years in the development of the technology and the data sheets, more and more manufacturers, I think, are far more aware of this effect now and are starting to specify the sort of conditions you should impose the gates to. They're far more
conservative.
Yeah, they're far more specific about it, because things that happen over a longer lifetime are a nightmare if you're trying to release products to the field. So the sort of the effects you've been describing on the webinar today, I think, underpin why they're perhaps being more conservative now with datasheet specifications, because we have to make sure we much more carefully control the gate than perhaps a few years ago we thought we had to.
Yeah, I mean, the key is that in order to measure this, you will need real life measurements. You will need field operation measurements. Yeah. So if you tell to a manufacturer, okay, these accelerated measurements that are 40 volts 1 week or 35 volts 10,000 hours, they are okay, and they just extrapolate that to, okay, if you bias your device with 40, you get this, 35, you get this. So that means that if you bias your device with 15 volts, your lifetime is going to be 100 years. You cannot spend 100 years with your gate at 15 volts to check if that's going to cause a problem. So that's the main issue, that when you're doing power cycling, you know that they're using delta T's of 100 degrees, 120 degrees, 80 degrees, 90 degrees. And then it takes around 1 month, 2 months to get the device to fail.
Yeah.
If it's just a matter of time, and then you require time that probably you don't have. And methodologies were quite important. So if you remember the slides, we were showing that you have to capture the peak shift. Imagine that you are doing, let's see, qualification of devices, and you have 1,000 devices that are stressed in your machine. And from the moment that you start characterizing the first to the moment that you are characterizing the last one, there is a long time. Then if you check the standards were also saying that time can happen, you can spend some time between stress and characterization. If the standard says that you can spend 1 hour, what happens during that hour? Here you have a lot of fast traps. So some people are proposing methodologies that can capture the stress properly after stress removal. They are proposing some kind of re-stress application to verify that things happen. Some people are saying that if you do the stress at 150, you should do the measurement at 150. Some people say that you should do the measurement at 150, but you still should cool down the device, keeping the bias, and do the measurement at ambient temperature again to see if there is anything there. Sure. Because temperature also affects the trap relaxation.
Okay, yeah, interesting. And is this a particular thing for silicon carbide? For example, if we took a normal silicon MOSFET, and took its gate drive voltage to real extremes. I mean, they're not with silicon. It's normally plus or minus about 20 or 30 volts. If we really widened that out from silicon, would we see similar effects in silicon, or is it purely a function of this being a silicon carbide device and silicon is completely immune?
I would say silicon was there, and then that depends a lot on the device. If you check BTI on silicon devices, that's mostly about, say, microelectronics and that stuff. But I've seen some papers where they report threshold voltage shifts and dip and recovery bound and dip and rebound, but they are using around, I think it was 60 to 80 volts on the gate.
So that's the interesting point, isn't it? Because what we're really saying there is this is sort of almost an inherent thing in power MOSFETs. It's just with silicon carbide, those thresholds are much closer to zero, or the behaviors, it's much more sensitive to gate drive than perhaps silicon is. But they do suffer similar effects, I guess. Because what we don't want to say, what we don't want to conclude is silicon carbide is bad here, because it's not. It's a fantastic technology.
No, I mean, it's just that you have to be aware of what's going on, and people are aware, and you have to do whatever they tell you to do.
Yeah, sure. So we're all learning, I guess, how to use this technology.
I mean, using 40 volts is great to stress the device and get this kind of measurements. But you're not going to drive your device with 40 volts. You're not going to apply minus 26 volts to your gate. So that sort of stuff. So
yeah,
I mean, if you check, it looks like it's plateauing, so it's not that bad. So probably just pre-screening, and people are reporting things. So I would say, as long as you manage to have consistency in shifts, and the manufacturers, they have, all the devices, they have the same trend. They have, if they just eliminate the traps, it's just a matter of trap density.
Yeah,
I mean, the first devices, they were really they were reporting massive shifts of threshold voltage.
Well, we saw that in the data sheets, very early silicon carbide data sheets. They didn't really share any concerns about that permanent negative gate drive, for example, but most manufacturers now stipulate on the data sheets that you shouldn't sit with a negative gate drive, and I guess it's for exactly the reasons you've been discussing today, Jose. Manufacturers and designers are just learning how to exploit this technology and implement reliable systems, and it's just a learning curve that everyone's going through to successfully use silicon carbide.
I mean, just think about that. Just a matter of time. If you tell the manufacturer, I need 10 years of field data that I have to bias the gate, the device will not be in the market yet.
Yeah, exactly.
So, but people are there. People want to use silicon carbide, and you can just listen to the manufacturer and do whatever they tell you to do. If they tell you don't use minus 15 volts, don't use minus 15 volts. If they tell you don't use voltages of 12 volts, 13 volts, to avoid that thermal runaway, don't do that. So that was probably the first challenge that they faced, was the suitable positive gate voltage. Then it was okay, now it's the suitable negative gate voltage. Now people are moving into, okay, we have to balance this. Do we understand what's going on?
Yeah.
But I think,
I guess the $1 million question is if we operate a silicon carbide MOSFET within the datasheet recommendation from the manufacturer, could we assume a similar reliability and lifetime for a silicon MOSFET driven within its datasheet recommendations? And I think probably the answer is we're getting close to that now, because people understand how to drive them properly. Would that be a fair statement, do you think?
I mean, you have to trust the manufacturers. If manufacturers say, this is the reliability test, this has been done, and we haven't measured this, who am I to say that's not there? So at the end, this is why they have the JD committee, JC70.
Yeah. Okay.
That they are working on qualification methodologies to check that, okay, this is done and this is right. So there's another question here. What type of gate protection circuit to be used to protect? I mean, you will need clamps. some people are using some Schottky clamps to limit the positive spike and negative spike. So that's the only thing that I can think of. Probably some ferrite beads to remove the ringing. But there are a lot of stuff. There's a lot of stuff there. But I would say, trust the regarding your question. Trust the manufacturer. They know more than us. So they probably have more man hours than in the labs. And
sure.
I mean, I still like silicon carbide. I really like.
Yeah, it's fantastic, especially the performance you can get at system level. I think the key thing here is that the more we're aware of some of these effects that you've described today, the better informed we are with how we then go about and design our real application circuit, and that's the value of understanding the knowledge you've been, the technical content you've been presenting today. Because they're not as simple as to drive as normal silicon MOSFETs, and I think that's a key conclusion, really.
Yeah, and then you still have, let's see, short circuit capability if you have if you require that. Avalanche, they are good, so that's always tricky there.
Excellent.
But well, I hope that you enjoyed the presentation. Not sure if this was a bit too technical or nothing new for you. So I hope that people enjoyed.
Yeah, we're always open to feedback, Jose and I. So if you think the level today was good for you, do let us know. If you think it was too much and too much technical detail, again, let us know, and then we can refine the technical content of what we produce in the next few webinars. Jose, is there anything, before I sum up, is there anything you would like to else to say on this?
I would say no. Probably, I think that my next webinar is on packaging. It's not going to be a hard packaging webinar. Is going to be mostly oriented to introduce condition monitoring. So what's the role of the Kelvin source and things like that, ringing and things like that. That should be interesting. So some comments there. So thanks for attending. I hope that I didn't bore you. Still use silicon carbide. I'm a big fan of silicon carbide. Don't use 40 volts on your gate or 26 volts.
Indeed, absolutely. Wise words. Thanks, Jose. And thank you, everybody, for joining today. Just to sum up, we're going to be moving on in the next two webinars to change focus slightly. We're going to be moving into high-performance magnetics design. I think that's on the next one is on the 6th of October. I think that's correct. And then the 13th as well. And we're going to shift that focus really because you have to make sure not only that you're using high performance semiconductor devices, but the rest of your circuit can keep pace with them as well. So if you've not registered for that, please do check out the registration links. You can register for the magnetics webinars as well. And we have Jose's stuff in it. I think you're then after the magnetics things, Jose, aren't you?
Yeah, I think so.
Okay, great.
But
Perfect.
it's just to mention that it's not going to be a hard packaging webinar. It's going to be mostly an introduction to condition monitoring from the point of view of packaging. So what degrades, what you check.
Yeah. Okay.
So explain a bit. If you explain condition monitoring without explaining packaging degradation, that's not easy to do. And I prefer to have two short webinars than a massive webinar. Okay. Hope that the pace today was fine.
It was great, Jose. Thank you.
Compared with.
Okay, thank you, everybody, for attending, and we hope to see you next time. Thank you very much. Bye-bye.
So, bye.